Good morning, everybody. This is Argonne 5th quantum computing tutorial, 4th day. I'm your host, Yuri Alexeev from Argonne National Lab. Today's speaker is Junior Liu from US Chicago. He's going to talk about quantum machine learning. Junior, it's all yours.
Okay, thank you very much. So let me share the screen and then it will stop your sharing. Okay, so let me share the screen. Can you see my screen?
Yes.
Good, yeah, so great. So welcome to the tutorial, and I'm very glad to be here. So to give give a presentation on some of my experience about quantum machine learning. So this talk is designed to be simple, and several things are, starting from scratch, and some of them conceptually would overlap with VQE talk, and has been presented before. But we will also introduce some unique features about quantum machine learning. So my name is Junior Liu. So I'm from University of Chicago. I'm supported by those 5 institutes. I'm also a scientific advisor of this company, which is called Qubit, where I will show you the code session and through the Qubit platform, but it's the same as you could also run it in Qiskit at all, also. So I will introduce that later. But yeah, so firstly, a brief introduction of myself is that currently I was a postdoc in University of Chicago together with IBM. It's in the Chicago Quantum Exchange. And before, I have a PhD in California Institute of Technology, Caltech, and with a theoretical physics PhD. And in the past, yeah, I was born a long time ago, but yeah, so okay. So let's start. And a very brief outline of my presentation today are some so it's the following. So firstly, because I'm starting from scratch, so I would introduce some basic notations and concepts about quantum information science in general. And then I will talk about variational based quantum machine learning specifically. And later I will introduce the so-called quantum kernel method, and including some basic knowledge of classical kernel method. Also, finally, I will give a brief introduction of quantum neurotechnic kernels that provide you a theory of quantum machine learning for the variational based quantum machine learning. And then finally, I will give the code presentation based on some code that could be run in Qiskit, Qiskit's quantum machine learning package. Okay, so if you have any questions, and you can ask me later. So good. So let's start. So firstly, and I will give a very brief introduction and a few minutes about quantum information science, and to make sure that everyone here are at the same page. So we are starting. So the best way, from my experience, to communicate things and from quantum to people outside of quantum is through mathematics. So I will define everything that improves in assuming that you know basic knowledge about mathematics, about linear algebra. So firstly, we're starting from a Hilbert space H, which is a linear space that allows inner products to be either finite or infinite dimensional. So for infinite dimensional, usually it happens to the case of continuous variable quantum computing. But in this talk, we will focus on spin-based quantum computation, which is usually finite dimensional Hilbert space with some inner products. And then usually for n qubit system, and the dimension of the Hilbert space is 2 to the n, and which is a direct product of a bunch of space c squared, where c is a complex space and with 2-dimensional complex space, and quantum states are vectors that is in the sense of linear algebra that is living in such a Hilbert space H. So we use a Dirac notation to represent quantum states, and we say that the vector in the in the Hilbert space is called the quantum states, That's called as psi. So and then so it is introduced, this abstract vector notation is introduced as this cat symbol, so-called cat symbol. And then this cat symbol, and basically you could do the basis expansion, and then by expanding it towards some computational basis where we denote them by I in the n qubit system, it could be range from 0 to 2 to the n minus 1. So in total, it was 2 to the n dimensional. And then you could also, in the sense of linear algebra, you could also define the so-called dual space, and which is this notation, and which is called Bra. So in a Dirac notation, and it's in a dual space, so you could define inner products, and also you could define an operator expectation value of O by just computing the bilinear form of O in terms of those two vectors phi and the curly phi. So that is basically the definition, and the definition of the linear product is very important later, that it gives you observables and expectation value of observables. In quantum mechanics, observables are defined as Hermitian metrics in a Hilbert space H. So when we measure some observables in some quantum states, so we usually mean that so we are observing, so they are eigenvalues of that Hermitian matrix. So let's say O, and you have let's say that you have 2 to the n number of eigenvalues, and if that means that for the observable O, you are able to measure this 2 to the n possible outcomes through a measurement. So, and then in quantum mechanics, there is an important thing which usually people call the Born rule. What it means for Born rule is that you could do the eigenvalue decomposition of the operator O, and in terms of its eigenvalue and also the eigenvector. So that means that we are decomposing using this notation. So we are decomposing a given observable O into the eigenspace. So for arbitrary quantum states, and then we could also do similar expansion, basis expansion, but expanding over this specific eigenvector of this Hermitian matrix O. And then the so-called Born rule, it means that we will have the probability phi squared, where phi is the expansion coefficient in front of each eigenvalue decomposition. And then we will have a phi I squared, which is a norm of this complex number. And then that will measure the probability that we have to observe an observable OI. So, which means that if we are in some physical state phi, and then the probability for obtaining the value of the observation OI is going to be phi squared. And then if this vector is normalized, then the sum of all phi I squares is going to be 1. So that's the rule of probability. And then the expectation value or a mean value of this measurement is given by the inner product or the bilinear form that I defined before. Okay, so I think that's almost all that what we need to know. And before we basically introduce what is the quantum machine learning. So, and moreover, more knowledge about this is the existence of entanglement. That, so because we allow this kind of inner product structure, so then we could define so-called Bell state. A given Bell state is given, for instance, here is an example of the Bell state. It's a direct product of two Hilbert subspaces. And what it means is that here in the first spin, I have 0 and 1. And here I have 1 and 0, and then I add it together. So in total, it is a normalized state vector. So based on the Born rule we introduced before, so the idea is that, so if we measure 0 in one location, and then we immediately know that another location is going to be 1. So, and similarly, if we measure one location, which is 1, and that means that another location is 0. And then both of them will have the equal probability, and which is 1 over 2. So this describes entanglement. So which is often the typical feature of many many application of quantum algorithms that could guarantee you some degree of quantum speed up. Okay, so quantum computing. So usually that means that evolution of quantum states that's given by, we know that, so firstly, evolution of quantum states. So it is given by some unitary operators. So quantum computing, so that means that we realize the arbitrary unitary operator in that Hilbert space using a small set of universal gates. And then quantum computing is that basically we are equipping those kind of small set of universal gates, and then that will represent in some precision some unitary operators. And then that basically describe an operation from one quantum state to the other quantum state, basically the evolution. And using this process, and we are saying that we are doing quantum computing and engineering those unitary U and bring one state to the other state is basically the computational power that we have in quantum computation. So the basic operation, just like the digital observation, digital manipulation, like and or and some basic gates. And in quantum computing, we similarly will have the quantum gates. And so for instance, so we will have those Pauli matrices. So, and they are some part of this small set of universal gates. So they are zero trace and also Hermitian matrices, and in the space of 2 times 2 complex space. And then we will metric space, and then we'll have those 3 matrices. So these are usually considered to be part of the basic universal gate, and we are assuming that we are able to manipulate them, manipulate them themselves, or manipulating like e to the I theta x, which is going to be a unitary operation, and x, y, and z themselves are also unitary operations. So also, and later, for the later convenience, we could define so-called a Pauli group. So Pauli group is some elements that are with a form, and the elements in the Pauli group are with the following form. It is a direct product of n copies of arbitrary Pauli matrices, and it could also be the identity matrix in 2 by 2 space. And then for an arbitrary combination, like here it is x, y, and it could also be z, an arbitrary combination of them. So it's going to be an element of the Pauli group. So they are redundancy defined in this notation in the Pauli group. But roughly speaking, you could regard it as a possibility 4 to the n, where n is the number of copies here. Usually that means number of qubits. And then for each location, and here you have 4 choices. You have x, y, z, and identity. So the total number of elements in the so-called defined Pauli group are has the element 4 to the n. So okay, so that is a very brief introduction of quantum information science and quantum computing that's going to be used in this talk, and later, and then we will jump to quantum machine learning. Okay, so quantum machine learning, so is an area that is highly in development. So that means that it is a very early and unmature field. And the things I'm saying, and maybe people realize that they are not applicable or they are wrong, and like a few years later. So that is by definition an area and in development. So it is very unmature. It is very promising, but it's still very unclear. So by definition, quantum machine learning is running machine learning algorithms in the quantum devices. So that means that we are combining 2 very hot technologies, and including machine learning and the quantum computing. They seems to be very promising. So combining them seems to be also very promising. However, so there are still some big picture problems usually we want to ask. So about basically the definition and the various perspectives of quantum machine learning. So firstly, what is quantum machine learning? So, and for different people, it might have different models and to define quantum machine learning model. So furthermore, so why we do quantum machine learning and why we prefer quantum machine learning instead of classical machine learning, and where is the quantum advantage? So furthermore, so what is the typical problems for quantum machine learning? Is there any prototype problems that we are interested in? And what is the quantum machine learning algorithms we are used to solve those typical problems? And if we are using the supervised learning, so we have to use data. So do we have a quantum database? Is there any quantum version of the database for quantum machine learning? Are the quantum database quantum states or just classical data? So can we do both? Or what is the advantage of doing quantum machine learning in a quantum database? So those are some big picture problems. So they can be answered in some degree, but it is not completely clear. And each of the questions will form some research directions. So usually as a summary for the most people, and when people talk about quantum machine learning, so there are usually like three possibilities. So the first one, especially recently, people like to talk about learnability and pack learning. So, and those are based on some very formal development in the last century. Before the time of so-called deep learning, people start to study the statistical learning theory. And it is a very beautiful theoretical framework that you could answer some theoretical questions. And for instance, like what is the learnability? How to define learnability for some given error and probability? Can you learn things for a given size of the database, and how to reconstruct a basic, for instance, a continuous function f? And what is the maximal allowed bound of complexity that's given the size of the database? So those are usually like a pack learning or statistical learning problems. And especially recently, and people extend them to the quantum regime, and they will bring important consequences, or one of them is so-called classical shadow and the shadow tomography that's useful for answer some of those kind of questions. And for instance, how to learn properties from a physical experiment. If the data itself is intrinsically quantum or it's classical, then how to do learning and how efficient it is to do learning, at least to the maximum bound. And usually if we are doing quantum version of them, and usually we need a long-term quantum devices, which means that we need error correction because those things probably needs a stable quantum memory. So, and if you're interested, we could talk further about this topic, but it is not the primary focus that we have in this current talk. So another type of machine learning or quantum machine learning problem is that people like to study some machine learning algorithm that is based on existing algorithms, like if it is Grover search, or it is HHL algorithm for solve the sparse matrix inversion. And as long as any of your classical algorithm that has any of those ingredients, and then we could adapt it and to make a hybrid quantum classical algorithm. So, and that means that imagine that you have a large classical task, and then you insert in the middle. So let's say sparse matrix inversion, and then you immediately move it to a quantum processor and do HHL and read it using some way, read the data. And then those are the things that we could imagine. So because usually, especially HHL, people consider it to be still in the regime of fault-tolerant quantum computing. So that means that without error correction, it will bring lots of errors, and we may not be able to use it. So the primary topic that has been focused in this current talk is about gradient descent-based learning, so which is based on variational algorithms and also the kernel methods. So those are like something very similar to VQE, and it could be applied both near term and long term. And then so in a NISC device, even if with noise, maybe it will be possibly give some advantage, or maybe not. But currently we are still not sure. And for the long term, we are also not sure if they could bring us advantage. But so those are something that we could immediately try and in the quantum devices and with some reasonable amount of error. So that's part of the reason that so I will presenting the talk today for the more practical and near-term implementable code-based lectures. But if you have any questions, we're also very interested in communicating with you on the first two topics. So let's make it more specific. For the variational-based quantum machine learning, so usually people talk about algorithms that is based on so-called variational quantum algorithms. So I think people probably have already heard of them from a few days ago by this VQE and part of the tutorial today. But basically for this kind of VQE used for machine learning is the same construction. So the idea is that you could equip a given unitary U to be a bunch of gates, WL, and then times e to the I theta x, where WL are some fixed gates. And for instance, here it is a simple example of variational quantum algorithm, and here it is a bunch of C naught. And W is not related to any classical trainable variable, and which means that it's fixed. And however, it has another part e to the I theta x. X is an element of the Pauli group I discussed a little bit earlier. So which is on the, in principle, it could be like on the 2 to the n dimensional space. And here specifically, I'm taking this to be x to be y, local y gate. And then so it's gonna be a bunch of rotation of in terms of y. Rotation means I to the theta times Pauli matrices y, and locally happens here. So this example is a diagrammatic picture of a general so-called variational quantum atoms. So, and then because it has classical observable theta, and then we could make this U and measure it at somewhere and make a loss function and perform a gradient descent. So over those classical variable theta, and the steps of those loss function is evaluated on the quantum devices, but the gradient descent is performed presumably in a classical computer. And then we could do this back and forth, and this is the spirit of VQE and also quantum variational quantum algorithms or quantum machine learning algorithms. So people have successful example that applied to so-called NISC quantum computational chemistry for VQE, quantum variational quantum eigensolver, and also quantum neural networks. So here we also call this construction quantum neural networks. If you put supervised data in, which I will talk a little later, and then we are able to do learning process to do supervised learning. So here is a specific example. So let's say that we are starting from a quantum state, and we are imagining that we have some classical data x delta. So where delta is the notation of some event space in the event space. So let's say it is I want to distinguish cat for a dog, and then x delta is a bunch of say vector of the pictures, vectorized version of the pictures, and then I make a so-called quantum feature map phi that's encoding the data x delta into some quantum states. So these things are, there are various ways to make this kind of state based on the given classical data. And a typical example is quantum random access memory, which allows you to bring such a classical data to the quantum to the quantum space, to the quantum Hilbert space. It could be classical. It could also be quantum in principle, where in a quantum case, we would consider quantum data. And x delta, for simplicity, we can also refer it to be classical. And then that means that we are bringing some classical data like pictures of cats and dogs and into some quantum space. And then we will construct the measurement. So this is the measurement protocol that I was introducing before, based on the Bourne rule. And then you can measure the operator OI. And after you act a unitary U, and which is given by this variational answers, and then acting on them, and then make an expectation value of this observable OI on that state. And then it will create some prediction. We usually call Z some prediction that's based on the trainable variable theta and the classical data x to x of delta. And then for simplicity, we will consider the mean square loss function. That's one of the most common loss functions that people have studied in classical machine learning. So which is that, let's say that we have a prediction Z, and then we have some label, and which is a data label. Let's say that if I'm in a training set, alpha tilde, where we have a tilde means that we are on the training set, and then we are differentiating, computing the difference between the prediction and the answer, where Y is the answer of cat and dog, for instance, and Z is the prediction. And then we square them and sum over all components and sum over all like a training set. And then summing them together, this will make you a loss function as a function of so-called trainable variable theta, and the evaluation of this loss function evolving the measurement in the quantum devices. And then we will call this quantity Y minus Z or Z minus 1, Y, so-called the residual training error, so epsilon, that we will briefly talk about it later. And then the gradient descent algorithm is defined as this equation. So define this fancy D of some quantity O as the difference between time step T plus 1 minus T. And then the gradient descent algorithm, classically, it's the same as classical computation, is that the difference update rule of the difference of two variational angle theta of L is given by minus eta times the derivative of the loss function over theta. And then the eta is called the learning rate, and usually it is it's a small positive number. And then the derivative is performed over this loss function L. And then so that is the definition of the gradient descent algorithm. So it's the same as classical. The only difference is that right now the loss function and its derivative is evaluated in the quantum devices. And then we will repeatedly doing this process by keep updating this variational angle theta, and hopefully we are able to minimize this loss function L. So this is a basic variational based quantum machine learning algorithm. So note that if we, let's say, put this dimension to be one dimensional, let's say, oh, we only have one data, X1, and then only one picture. And for instance, and then the problem is reduced to the VQE case. It's the same as VQE, but with only one single supervised data. And then, but if you have multiple data, it's a general supervised quantum machine learning problem. Okay, so, and then I'm happy to talk about a little bit more advanced, so which is called the quantum kernel method. So what is the quantum kernel method? So let's forget about quantum and firstly introduce what is kernel method. So let's consider we are making predictions just like in the way that we used before. So let's again use the notation with tilde, means the data and like alpha and beta. With tilde means that it is in a training set, and then alpha, and I mean without tilde, alpha and beta, it means that a general data point. So a simple so-called linear model, so is that we have a prediction that is basically given by a linear sum or linear coefficient summing over all the training set. So, and then here we have a trainable variable theta to the beta tilde. And we also have this function k. K is a function of x alpha and x beta tilde. And note that K, you can understand it as a matrix with matrix input alpha and beta. So this is a matrix that is established on an event space, or you can call it a metric or a bilinear form. And it's positive, semi-definite, and symmetric. If it is positive, semi-definite, and symmetric, then it is called a kernel. So, and here theta, it means trainable variable, and x again, it means theta, and z means the prediction. So there are theorems that tells you that if you have a positive, semi-definite, and a symmetric matrix, this will defines automatically, it will specify a linear space with an inner product structure K, specified by K. So up to diffeomorphism, so that is a unique space. So combining the definition of a Hilbert space together, so that means that we have a unique dual abstract Hilbert space for a given K. I use the term abstract Hilbert space. It just means that it's purely mathematical. So it may not be related to physics. It's not really the physical Hilbert space at the current point. And for a given arbitrary function K, as long as it is positive, semi-definite, and symmetrical Hermitian, so you could define a linear space and with the equipped inner product given by K. Okay, so this is just a mathematical fact. And then, so there is the so-called representative theorem. So, which says that for an arbitrary nonlinear function we want to learn, and we want to do gradient descent to machine learning, for instance, there always exists a kernel that established with a Hilbert space in some sufficiently high dimensions, such that the function is learnable, and it's basically kind of dual to some arbitrary construction of the classical neural network you could imagine. So basically, this kernel method could be as universal as usual neural networks, as long as you somehow construct a so-called feature map that maps this data X to some Hilbert space, and then you evaluate its inner product. And then if this Hilbert space itself is sufficiently high dimensional, you could have a very high dimensional abstract function. And then, so you will get the same performance as the usual neural networks. So if you are interested, and because it is a classical, it's related to classical background, here it is just a sketch, but you could look at some, say, statistical learning theory book or some mathematics book that talks about the kernel method in machine learning and linear regression. So basically, the kernel method will transfer a nonlinear problem of a nonlinear function to some linear regression problem. And then as long as, so only requirement or drawback we have to pay is that kernel or that linear regression problem is established in some higher dimensional space. So for instance, so there is so-called the Gaussian kernel, so which is given by this quantity, and it's just exponentially decaying, and here it has a square, so it is so-called the Gaussian kernel, and it's classical. And you could a homework is that you could prove that this Gaussian kernel is positive, semi-definite, and symmetric. I think symmetric is naive. The question is how to prove it positive, semi-definite in the event space. So where I will leave it to you as a homework. So, and then for the quantum kernel method, so it is natural that we could imagine the abstract version of the Hilbert space, which is basically the linear space with some specific version of inner products that could be naturally understood as the physical Hilbert space. So for instance, so you could define this small k q and to be some, let's say, inner product where this phi is the same as a quantum feature map that I have introduced before. And then you could compute the naive inner product or inner product square. And by, as I mentioned before, this corresponds to measurement based on the Born rule. And you could compute those to both of the quantities by physical observations and in the quantum devices. And both of them are constructible. And in fact, both of them are positive, semi-definite, and symmetric. So that in that sense, and quantum space is something very natural, and to be a good space for you to do kernel methods in classical machine learning. But right now, as long as you bring it to a high dimensional enough Hilbert space, in principle, it will work based on representative theorem. So this kind of construction, in principle, it has enough expressibility, and because we will have a large amount of Hilbert space, in principle, with large amount of qubits, so these things might be more efficient and outperform classical machine learning in some case. And in fact, there is a rigorous example where people prove that this kind of kernel has exponential advantage against the classical machine learning method. So, which is approved by the first author is Rin-Chao Liu, and in a few, I think like 2 or 3 years ago in Nature Physics. So, and then there is a homework that you can also prove that both of the kernels are positive, semi-definite, and symmetric. Where first one is not exactly symmetric but Hermitian, and the second one is positive, semi-definite, and also symmetric. So for the first kernel, it is naive to prove. It's pretty simple to prove it's positive, semi-definite. But for the second one, it's a little non-trivial. So, but in principle, and then I can just state the conclusion is that both of them are positive, semi-definite, and symmetric. So they could naturally be assigned as the kernel in the kernel method. And as I mentioned before, the abstract version of the Hilbert space could be naturally the physical Hilbert space. So that naturally brings you quantum computation. Okay, so finally, so I will give a very brief introduction of so-called quantum neural-tensor kernel. So which is a connection between the kernel method and the gradient descent method of the variational algorithm I was mentioning before. So it was constructed also inspired by classical people. In order to understand it, so let's start from a simple example, which is a optimization or VQE type example, that you have some variational assets that is acting on some fixed states. And so there is, and then you could, based on it, you could create a so-called loss function. And as it defined, so before, this loss function could be the difference between the prediction and the answer. You could set it to 0, for instance, in the VQE case, and then you could square it, and then this is basically just a mean square loss. So, and then, so you could perform the gradient descent algorithm, as I mentioned before, in the variational-based quantum machine learning algorithms. Like this is a gradient descent rule. But instead of considering the gradient descent rule of variational angle theta, and we could bring this equation back to the so-called receiver training error epsilon, which is the difference between the prediction and the answer. So doing a Taylor expansion, the change of the two steps of the receiver training error epsilon is given by a sum over the leading order Taylor expansion, assuming the learning rate eta is small, is given by the epsilon divided by the theta times the fancy d of the theta. So where theta is this is just a change of two steps of the variational angle, and with this Taylor expansion term and the derivative term. And then bringing this equation in the form of the loss function back to here to the derivative, and then you will get this. So you can define this quantity, and which is a sum over the derivative of the receiver training error epsilon divided by variational angle theta. You make a square of them, and then you sum it with all the trainable variable theta. And this quantity itself is called the quantum neural-tensor kernel. So it's in fact, here it is a reduced version because we didn't put any supervised data. So the problem itself, so it is a so one-dimensional, could be regarded as a one-dimensional problem. So we call it a kernel, but it is in fact a 1-by-1 matrix. But in general, so for the machine learning type problem with supervised data, and then you could similarly construct a quantum version of neural tiny kernel. And in fact, so it is right now it becomes a matrix instead of a 1x1 matrix, which is a number. And in this case, so those equations or those gradient descent and those equations becomes vector equation and matrix times vector equation. Where here K could be defined as a matrix. It's a matrix expanded over the data space delta with indices delta and alpha tilde, where I and I prime are dimensionality of the outputs. You could set them to be 1. For instance, if you only want to distinguish, let's say, cats and dog, and it's gonna be nothing, the output is 0 or 1, so it is only 1-dimensional. But here it is a formula, and for a general higher dimensional example, but more importantly, this kernel is the same as the kernel that we talked about before. It's a matrix over the event space. And you can also easily prove that this guy is positive, definite, and symmetric. So that means that this will be a natural kernel in the same sense of the kernel method. So note that the quantum neural tiny kernel is an emergent kernel and during gradient descent. So that means that it is originally here it is a nonlinear problem because this encoding and this parameterization of the state is nonlinear in the variational angle theta. However, so it is nonlinear originally, but from the gradient descent, but it is some emergent kernel that is for the kernel regression, which is a linear. And as I mentioned, it's positive, semi-definite, and symmetric. You can prove it as a homework. And also, it is generally changing during gradient descent. So it is not a fixed kernel that in general, because of these or rational residual training error epsilon is a function that's depending on the variational angle theta. So it's going to be a changing matrices, gradually changing and generically changing during the gradient descent process. So in the limit, and finally, in a brief comment is that in the limit where kernels are almost constant, we could get a predictable dynamics of gradient descent. So that's because if this thing is a constant, then approximately this problem is a linear regression problem. So because your kernel is not changing at all. So, and then we could exactly solve this recursive equation to give an exponentially decaying performance of a residual training error. And then, so that's saying itself. So that's predictable because we know that how to estimate the error of the linear regression problem and a kernel regression problem. So it brings back to an exact solution of the gradient descent problems. So, and then, so for this, because it is really around the cutting edge scale of the research. So if you're interested, I could recommend you to look at some of my papers in this area about establishing the quantum neural tiny kernel, which is correspondence from the classical from the kernel method, quantum kernel method, and the variational quantum algorithms. So these are about the papers. It is greatly appreciated if you are interested in reading our paper. So I think that's all about my tutorial today. And from now to so for the verbal presentation tutorial, and later we will switch to the coding session. But right now, feel free to ask me any questions. So, is there any questions?
Yes, so feel free to unmute yourself or just type question in chat.
Yeah, so in any time you can type question in chat. And then I didn't see any of the typings in chat. I expect that there will be more questions, but so maybe should we switch off the recording that people could ask the question more free? I don't know, so maybe we should not. So
no, we can always cut it out later. So
yeah,
let's
yeah, sure.
keep recording rolling.
Yeah, so I was imagining that a large part of this talk was based on some will be questions, and people would ask questions. So this we still have a few minutes, and okay. So
Yeah, no, but I can still maybe ask some questions. So, here you go. You have Reed.
yeah, so yeah,
Reed,
so
please go ahead.
great. So do you have questions?
Yeah. So okay, just this I don't have like I don't have a strong background in a machine learning, but I guess I was just have a notation question.
Yeah.
So I think earlier in when you were in the derivation, you were going over I think it was variational based quantum algorithm slide.
Yes.
Yeah. So you emphasized that like the theta L term
Yeah.
is treated as a classical observable. I guess
classical variable. Yeah.
Yeah, I guess I was just kind of curious on what that's meant to be interpreted as. And if you could just elaborate on that a bit more.
Yeah, so good. So I mean, so this is a question. So the question is, what is this theta? So the reason that I call it a classical variable is basically because here we imagining that we are in a quantum circuit, and then say that we have some rotation angle. Those are programmable gate that if you specify theta, which is classical between 0 and 2 pi, and then we could implement such a gate for you. So it's so this gate itself is parameterized by classical variables, and then we are doing gradient descent for those classical variables. So and in this case, so this is what I mean by this classical, because theta is just a number, so it is just between 0 and 2 pi, for instance. And then because it's a natural way to parameterize e to the I theta x, y, and z, where x, y, and z are Pauli's. So usually it's very commonly used this kind of rotation gates. And then we treat it as a classical variable because it does not correspond to any quantum observable.
Oh, I see. So like, can you still interpret it as sort of like an angle, I guess? Like,
yeah, it's something like the angle because it's e to the I theta x. And then so it's, I mean, it's something like, for instance, the number of gates, like a number of trainable gates, L. So L is a classical variable, right? So so equations
right.
itself, it has classical variables. Even if it is a quantum circuit, representing a quantum circuit, we are specifying theta as I mean, classical angles that you could be, I mean, intrinsically made in your devices. And those thetas are also programmable. And in the sense that, let's say you want to change it to be pi over 3 to be pi over 4, it's fine. And you tell the experimentalist and they will change it for you.
Gotcha. Yeah, thank you. Yeah, that clears up.
You're welcome. Yeah.
Yeah, so
is there any further questions?
Yeah, maybe Eugenio, maybe a related question to that quantum circuit. As you can imagine, there are variety of ways, right, how you can construct such a quantum circuit. My first immediate reaction would be actually, I think you touched best that it's not to restrict yourself to just Ry. I'll add actually Rx and Rz gates as well to give you like a maximum flexibility, essentially.
Yeah.
Explore
Yes.
Hilbert space.
Yeah. So you could, I mean, in general, I mean, so Rx, Ry, and Rz are type of the gates you could choose, but you could also choose other gates as long as you could parameterize it. So let's say you choose Clifford. For instance, there are in fact a paper of Fred Chang, and which is changing this X to be Clifford. Instead of the Pauli group, they consider a Clifford group, and they do it using e to the I theta times a Clifford matrix. And then you could do, I mean, other things as long as it's allowed. Like you could even do S gate and T gate, and then you find some way to parameterize it, and then it's basically similar. But here, and usually people create computational hardware efficient answers is through the Pauli matrices, and they have the most experience.
I see. I see. Well, also related observation. Obviously, it actually depends on the hardware, right? Where you want to run.
Yes.
So I would imagine you probably want to use native gates, right? Here.
Right. Right. So, right. So this, I mean, to obtain this kind of quantity, and that's highly depending on devices. And then currently we are several like system like superconducting qubits and some other systems that could realize you evaluate this kind of prediction. And usually when you estimate the expectation value of the observable, you could use, for instance, like a phase estimation or some other type algorithms to compute the eigenvalues or doing other things. And those are all, I mean, established algorithms. So at least in superconducting qubits, and for ion traps, we may have different algorithms, but I mean, and those things are observable and experimentally detectable in the quantum devices. And a specific notice is that if you say that you don't want to compute the inner product square, which is a probability, instead you want to compute this kind of inner product itself, it's also computable and using a little more complex version of the Hadamard test. But this require, swap test. But this require a control gate. So you have to make a control and between this X and Y. But those things are X alpha and X beta. But those things are also doable in the hardware.
Okay, thank you. Any other questions?
So I know with other more classical machine learning models, one issue that you want to focus on and document is your machine learning's model and its robustness against changes and variations to its input. And I would imagine with quantum computers, due to their sensitivity to noise and error effectively, that requires some modification in order to cause them to be more robust. Is that modification on on the level of modifying the circuit that you use for your parameterized like machine learning network, or is that like a post-processing step?
That's I mean, that's a great question. I mean, thank you. That's a very good question. So for classical machine learning, so some of the algorithms happens in algorithm level and using gradient descent, it is robust. And then so what we hope in the near term, that is part of the reason that why we run those variational type of algorithms in the near term, is because we hope that the algorithm itself will have the robustness, because they follow similar rules and they are both parameterized. They do classical gradient descent. So we hope that the quantum devices, so they are able to, so even if they have some noise, and the prediction might be noise resilient. So in a sense that, okay, so even if it has some noise, does not matter that much. My machine is still efficient or even better. So a typical example is the stochastic gradient descent type of algorithm. So that people shows that, I mean, in some degree, adding this randomness or adding the noise will be helpful for the convergence of the algorithm. So, and then we hope that at a similar level, quantum machines will also do it. And they will be not only like the I mean, let's say the measurement noise, but also the hardware noise. And if it could be modeled as some random number that's going to be similar to the stochastic gradient descent, then people show that, I mean, so it could be as good as stochastic gradient descent, which is like noise resilient. So the reason of noise resilience in classical machine learning algorithms is kind of why people want to try variational algorithm in the near term. But however, so in the long term, so if we want to do, for instance, like HHL or some other like universal quantum algorithms with stable quantum memory and those kind of things, if you want to do machine learning, you have to do fault-tolerant quantum computation. But in the near term, we are taking advantage of noise robustness of the algorithm itself to make the result to be stable against quantum noise. And maybe we will find that in some sense, and the noise could also help us. So that's the answer to the question.
Cool. Thank you.
Don't see any other questions. Maybe you can actually take a 5-minute break.
Yes, sure. We can take a 5-minute break, and I will give a very quick. I mean, I mean, because I thought that our talk today is mostly about the question answering. So I thought that so I didn't prepare that much material for the coding session. But I mean, during that step, and if you have further questions, you could of course ask me. And the code itself is running, could be running in the Qiskit platform together with this new package called Qiskit machine learning. So yeah, so right now let's have a 5 minutes break. We will be back in let's say 11, and then we can discuss again. Okay, so we are back. So are we ready?
Yes, go ahead.
Sorry.
Go ahead.
Okay, good. Yeah, so let me try to share the screen. So, okay, so let's start again. So here the slides has been finished. So here, sorry. So here we are mostly focused on this kernel method. So quantum kernel method. So, and then, so you can, so for the related papers, so it is based on this, I think, published in Nature, this paper by IBM, the so-called supervised learning with quantum enhanced feature spaces. And so this is one of the first paper, and probably no one of the first paper that introduced the kernel method and apply it, realizing that kernel could be used to do a quantum kernel could be used to do machine learning. Yeah.
Junior, can you maybe link it in the chat, this paper?
So yeah, so I can send it into the chat. Yeah, sorry. So maybe we can do it later. So or I actually don't know how to open the chats. So okay, so I can do it later. So this is the early paper that we have. So the code I will show today is based on this paper. So, and also there is another, for your interest, there is another paper, and it's also the slides by Yunchao Liu. And as I mentioned before, they prove a rigorous and robust quantum speedup in supervised machine learning based on this kernel method. So I think the core person that I think also established this subject is Chris Tan in IBM. So yeah, also, okay, so let me, so Joe already shared this paper. So the code is based on the Qiskit that they have already coded up, most of them, and released them already. So the tool that I'm using today is so-called QBread for demonstrating your code. And QBread is a startup supported by Chicago Quantum Exchange and locally here. And then it has this online code platform that could run you many programming language. And instead of here, I'm using Qiskit, but you could also switch to other kernels. And then it's gonna be able to, I mean, combine all the quantum language together. But here I'm using it specifically for Qiskit machine learning. So here we only require Qiskit and also Qiskit machine learning. So this is an independent package at the current stage of Qiskit. So please install both of them. And but before that, I hope that you could upgrade your Python to be the most Python 3 to be the most recent version, and otherwise that you might have some like a version conflict or so on. So
Junior, before you go
yeah.
too far, did you upload this code into GitHub?
I already uploaded them. Yep.
Okay.
So the code itself, I use QBread, the platform, but it's my personal preference and it's free if you want to use it. But you could also use Jupyter Notebook. It's gonna be the same code. So, but please install Qiskit quantum machine learning, Qiskit machine learning, and also Qiskit itself. And this Qiskit machine learning is new package. It's a new package. And also it could tolerate a combination with PyTouch, and which is one of the most commonly used platform for classical machine learning. So, and then, so let's start to run this simple code, which is for doing gradient descent, doing the kernel method. So, and then, so the starting point of this code is that here it is in a two-dimensional example. So there is a function which is so-called ad hoc data, and in this Qiskit machine learning, that could create you some sort of artificial kind of data set. That this data set is specifically here. We are showing the example of let's say of the ad hoc data set for classification. that we have the two-dimensional data that is generated from this code, and then it's a little ad hoc in the sense that I mean, so it's a it's a classification problem that part of the dots are red and part of the dots are blue, but this kind of data set is specifically created for applying this algorithm, so it has a good convergence. But in general, it works also kind of okay, and for their answers, and they have some and then let's imagine that we have such a data set, and then we have some sort of let's say training data and test data for the classification problem, blue or red, and then each time, so this function might generate you some new, some new data, and if you rerun them, it's gonna generate you new data. And here it is a bunch of new data, and I'm just now rerunning it in the real time. And so this is basically the data set. And then later we are going to create the feature map. So here specifically, we are using some this so-called ZZ feature map, which is some square root kind of function of x0 and x1. And then so x0 and x1 are input of this two-dimensional data. They take a square root of something like that and then make it to a quantum state or unitaries, which we call it ZZ feature map by parameterized by two Z's, but it's also a function that's internal in the Qiskit machine, Qiskit circuit. So they already have this ZZ feature map. So and then so here is a simple, very simple code that draws you implement and draws you the feature map. So let's wait for a few minutes. It's still running. Yeah, here it's a circuit diagram of this simple feature map, and here it has. In this simple case, very reduced case, it has only one trainable parameter theta. And then here in the simple code, we are using the IR simulator for the state vector simulator. And so it is not really a quantum computer, just some fake simulation. But for the state vector simulator, if you want to introduce a noise, you can also download the noise data and then try to simulate the noise also in Qiskit or also in here. It's also fine to use it. And then, so they have an internal kernel function that has this backend, including this quantum instance backend, and also the user parameters, and also the feature map we defined before, which is defined at FM. And this is this quantum kernel that they could create. And then you could also set up the optimizer that because we are using the linear regression, so we choose this SPSSA optimizer, and with some given some versions of the learning rate and something like that. And then we could make a quantum kernel trainer, and based on this optimizer, and we start from some rational angles, which is some versions of the initial point. And then we use supportive vector classifier loss, and this is some sort of a loss function. And then we are creating a quantum kernel in this kernel method. And then so here it will start to train, and it has some x and y axis, and also it have and then after you train, and then you might get a optimized kernel. So after you train, so actually the kernel itself, it has some trainable parameter, and then so which is a function of theta, and because it's about a feature map. And then after you get optimized the kernel, it's gonna print you the results. So let me run it. Oh, sorry, so I didn't define this so-called callback function. So we're in this gradient descent process, usually we define callback to give you the feedback of, say, that you want to output the number of some variational angles, something like that. So you see here we set a callback function, and then here is this optimizer and quantum kernel, and then you can train them train this quantum kernel. So and which is defined here. And after you train, you get optimized the quantum kernel. So let's run it, and it takes a few minutes. And then, so after you optimize this quantum kernel, because it's also includes a gradient descent for the feature map with a variational angle theta, and then you can use it for classification. And because you already have this kernel, so you could just compute the inner product, and this we choose the angle, and then it's computing the inner product. You could compute it by measurement, and then you can test how generalized your kernel is. So basically, you use the training data itself to construct the kernel, and you test how the performance is on the test set. And then so here is it's such a test for optimize the kernel. And then so here they have some measure of the output of the score, and for that gives you a score, which is sort of an accuracy. And then you can print this accuracy right now, and it needs some sort of metrics that you can define it by yourself, or you can also define some other metric. And it's some sort of an internal function. And then here, this metric score is test is 0.7, and if it is 1, then it's best. So 0.7 is okay. And then, so here is a plot for printing some properties of the kernel. So here, this is a matrix diagram of the kernel. That's gonna be this. I believe it's an optimized kernel, and yeah, it's an optimized kernel evaluated on the training space. So you can print the kernel diagram, and then specifically there is a line in the middle because I mean it's a diagonal part that should always be 1. So remember the definition of the kernel. So if the kernel is diagonal, so that means that two data are the same. So the diagonal elements are always 1 in this normalized kernel. And then the off diagonal elements has the information about the state overlap kernel. So of those different input events in the event space. So here it's this optimized kernel, and here is shows the gradient descent process, and which is about the loss function, and from a few number of iterations. And I think I already explained. So all this detail about this kernel method. So, and then you could play with the code by yourself, or you could search for quantum Qiskit kernel method, and then there are some other codes as well. So this so-called kernel machine learning, but this code itself, and it also has a kernel, but they didn't use that much effort to do gradient descent and training. But they also constructed the kernel, and you could also run this also, and they have a similar structure. They also print this kernel metrics. And they are also, it can not only be applied to classification, but also clustering algorithm. And then it's some, I mean, clustering algorithm that you could do. And they also have some version of the kernel. So, and all those codes have similar spirit. And if you are interested, you can play it a little bit. Or instead, you could also try VQE. For the machine learning tutorial, so they have quantum neural networks and also some other things, and especially for VQE, and I believe that they have lots of resources. And for instance, the quantum neural networks. And I think that's all that I want to present today. And right now it's a time leave for questions. And then I will give the link of the code that I was walking through just now. So including the quantum neural network and also especially quantum kernel method for machine learning application. And that is the primary code that I was using. And also there is another one, which is for quantum kernel method, quantum kernel machine learning. Yeah, sorry. So I should send it to everyone. Yeah. So do you have any questions?
Don't see any questions. We can wrap it up earlier today. But Genio, maybe can you provide your email in the chat, so if people have questions, we'll just maybe send you email.
Yes. So I'm sending the email address and in the chat. So it's a Gmail address, or you could use my Chicago address. And also, right, so feel free to ask me questions on any time. So I expect that there will be many questions. So I didn't realize that the time plots are a little empty. And if you have, especially if you have any feedback about our work and also about me. So I previously thought that I should also give a, tutorial about or a code about quantum neural kernel, but maybe that is a little advanced. So, but if you're curious about that coding, and feel free to ask me in person. Yeah.
All right. So, Genio, thank you very much for the presentation. It was very useful and interesting.
Thank you. Yeah. Thank you for inviting me, and also thank you for the attendance of everyone.
Yes, thank you, everybody. So we are going to resume tomorrow. Tomorrow at 10 a.m. Central, Daniel Lykov, my graduate student, will give a presentation about quantum noise, introduction to quantum noise, and how to deal with quantum noise using error correction and error mitigation techniques. So we'll see everybody tomorrow.